So the last topic we covered in this chapter was to do with RLC circuits, where we have resistances, capacitors, and inductors hooked up in series. So what we're told is that we have a resistance of 9.9 kilo ohms. So let me go ahead right away, multiply by 1,000, so it's 9,900 ohms. The capacitance is 0.15 microfarads, so that is 1.5 times 10 to the minus 7 farads. And an inductance of 25 millihenries. So I divide by 1,000, I get 0.025 henries. And it's very important when you do these problems, straight away convert them into the base units of ohms, farads, and henries. Okay, so then we're told that the generator supplies an RMS voltage. So let's call that VRMS of 115 volts at a frequency F of 60.0 hertz. All right, so I want to know at that frequency, what's the inductive and the capacitive reactance? And there I'm just going to plug and chug into my equation. So XC, the equation is 1 over omega C, and XL, the equation is omega L. Remember, X is the reactance, and has a unit of ohms. So omega is, let me do it over on the side, omega is 2 pi times F, and we're given F, so it's going to be 2 pi times 60, so that's 377 radians per second. Now remember, 60 hertz is the basic frequency that comes out of your wall plug. All right, so I've got 1 over omega C, so 1 over 377 times 1.5 times 10 to the minus 7. And so you can see it's important here that I've converted that to the correct units for the capacitance, and I get 17,684 ohms. And let's see, I should take that to 2 sig fig, so I should say 18,000 ohms. All right, XL is equal to omega times L, and now I can just again plug and chug. Omega 377, L is 0.025, and I get 9.425, or approximately 9.4 ohms. So the capacitor at this low frequency has a much bigger resistance than the inductor does. All right, so there's my answers for part A. For part B, I want to know what's the total impedance of the circuit. So impedance, that's Z. And Z is equal to the square root of R squared plus XL minus XC squared. And since we're squaring this, it doesn't matter whether I put XC minus XL or XL minus XC. All right, so now I have all my numbers. I just have to plug and chug. All right, so R is 9,900 squared plus 17,684 minus 9.425 squared. So you can see when I'm doing this calculation, I take my unrounded numbers from part A for the reactances and I put them in there. All right, so when I do that, I get 20,258 ohms, and I should round that to 2 sig fig, so 20,000 ohms. So to make it actually look like it's 2 sig figs, that should be 2.0 times 10 to the 4 ohms. Excuse me. All right, so next thing is, if I were to change the frequency, increase the frequency, what would happen is that the capacitive reactance would go down, the reactance for the inductor would go up, and eventually at some point the two would cancel each other out. I'd have the smallest total impedance of the circuit, and I would have the highest current. And that point's called the resonant frequency. So at the point where we have the resonant frequency, XC is equal to XL. And if I put those two equations equal to each other, So 1 over omega c is equal to omega L. And I solve for omega, I get omega is equal to 1 over the square root of L times C. And so I just have to plug in my value for the reactance, 0.025, sorry, for the inductance, 0.025 times the capacitance, which it was 1.5 times 10 to the minus 7 farads. And I get 16,330 radians per second. All right, so now this is omega. I'm probably being asked for the frequency. So here it doesn't actually say whether it wants F or omega, but if the problem asks for the frequency in hertz, I would have to find F. So remember, omega is equal to 2 pi F. So that means F is equal to omega over 2 pi. So I'm going to take my 16,330, divide it by 2 pi, and I get a value of 2,600 hertz. So on the problem, the way that this is stated, I would have accepted either because I didn't state whether it had to be in hertz or in radians per second. But if the problem were to ask you to what's the resonant frequency in hertz, then you would have to do that last conversion.